In this video, we will talk about how to compute partial derivatives. So I want to begin with the definition of what a partial derivative is, very formally. So if I let f of x comma y be a function, then del f del x. So this is the partial derivative of f with respect to the variable x. And there's a limit definition for what this is. It's the limit as h approaches 0. And it's really similar to the limit definition of a single variable function. There's an h on the bottom, and there's f of something minus f of something on the top. But in this case, we have a multivariable function. So instead of this second thing just being f of x, it's going to be f of x comma y. Okay, but when we take the partial derivative with respect to x, as we saw in the last video, what that means is we're holding y constant. We're not letting y vary. So the y coordinate even here should be the same. It should just be y. But we are letting the x vary. So for the x coordinate, we will write x plus h. And that's, let me just space it out a little bit more. X plus h comma y. That's the limit definition of the partial derivative with respect to x. So this is a really similar definition for del f del y. It's the limit as h approaches 0, f of x comma y plus h minus f of x comma y all over h. Okay, and if I had a function of 3 or more variables, we could generalize these limit definitions. So we could generalize these for 3 plus variable functions if we needed to. All right, so I'm going to focus the rest of this video on actually computing some partial derivatives. Okay, so in practice, if we want to compute, first let's do del f del x. What we do is we treat x as a variable and hold other variables, any other variables that are in the function, constant. So if I have a 2-variable function, as we did up here in this definition, I would just be holding the y constant when I find the x partial derivative. Okay, so similarly, if I want to find the partial with respect to y, we would treat y as a variable and hold any other variables constant. All right, so let's do an example to see what this looks like in practice. So here's the first example. Let's say f of x comma y is 20 minus x squared minus 2y squared. And I want to find the partial derivatives with respect to x and with respect to y at the point 1, comma 2, comma 15. So that means x is 1, y is 2. And, oh, whoops, I think there's a mistake here. This shouldn't be 15, it should be 11. The way I get the z coordinate is I would plug in 1 for the x, I would plug in 2 for the y, and that gives me 20 minus 1 minus 8, and that gives me 11. All right, so let's find these partial derivatives. All right, so let's start with a partial derivative with respect to x. So when we do this, the 20 is a constant, so that derivative is 0. When we take the derivative of minus x squared, because we're taking the partial with respect to the variable x, that means I do treat x as a variable. So the derivative of that is just minus 2x. Okay, but then when I get to the minus 2y squared, that gets treated as a constant. When I take the partial derivative with respect to x, we are treating all other variables, that includes y, as a constant. And the derivative of a constant would be 0. So I would get minus 0 there. That is super, super important. If you're unclear on why this is 0, I definitely encourage you to pause the video and think about that on your own for about 30 seconds. We'll see that a bunch over the course of this video and the next video. Okay, so we'll get plenty of opportunities to practice this and get used to it. All right, so simplifying this, we just have negative 2x. All right, but we wanted to evaluate this and plug in x is 1 and y is 2. I don't write the z-coordinate here. Actually, let me say it this way. I don't need to write the z-coordinate here because with my function is a function of two variables. There's an x and there's a y. So the input for my function is it just consists of the point that has the x-coordinate and the y-coordinate. So if I plug that in, we'll get negative 2 times 1, which is negative 2. All right, so that's the partial derivative with respect to x at this point. All right, so next let's do the partial of f with respect to y. So if we do it with respect to y, so the 20 still gets treated as a constant, so the derivative of that is 0. Now I'm treating y as the variable and x as a constant. That means minus x squared is a constant, so its derivative should be 0. So minus 0, and then when I take the derivative of minus 2y squared, now I am treating y as a variable, so I get minus 4y. Awesome, now let's plug in our point. So we'll get del f del y, whoops, let's plug in the point. X is 1 and y is 2. If we plug that in, we get negative 4 times 2 plugging in for y, and that's negative 8. Okay, so those are our partial derivatives right there. So one thing that I want to note about this is, in general, del f del x and del f del y are different. So in general, in practice, the partial derivatives with respect to x and the partial derivative with respect to y, they're going to be different. So now there might be certain exceptions where they're the same, but in general, in most cases, they're going to be different. And that showed up here in this example. All right, so next I want to just talk about some notation to talk about partial derivatives. So we can write the partial of f with respect to x in the following ways. So there are maybe 3 other common notations that we'll see for this. So sometimes when I have a variable of 2 functions, we call f z. And if we call f z, we could write it as dz dx. So that's specifically for a function of 2 variables. I could also write, there's sort of like a version of the prime notation, if you remember from calculus. If you remember from calculus, there's like a df dx notation, and there's also like a prime notation. So the version of prime notation for partial derivatives is we write f, and then we write the variable that we're taking the derivative with respect to as a subscript. So I write fx like this. Okay, and then again, if I have a function of 2 variables, we can write the f as z. So I could also write this as zx. All right, so we have these common notations to represent the partial derivative with respect to x. So we could similarly write the partial derivative with respect to y. All right, let's look at another example. So in example 2, we have this function g in terms of 3 variables, and we want to find all first-order partials. And first order just means take the partial derivative once. In the next video, we'll talk about how to find second-order partial derivatives. There, we'll take the partial derivative twice. So we need all of these. So let's start with partial with respect to x. And using our new notation, I'll write g subscript x. That means the partial of g with respect to x. All right, so to take the derivative of this e term, I need chain rule. We'll get e to that stuff, x over y, times the derivative of the exponent. And to deal with this exponent, I can actually avoid quotient rule if I keep in mind that we're taking the partial with respect to x, which means y gets treated as a constant. So I can rewrite this fraction and move that y to the front and get 1 over y in front times x. because now the 1 over y gets treated as a constant. So when I do the partial with respect to x, of the x term, that's just going to be 1. And the 1 over y is a constant multiplying that. So that'll just remain there. So that partial derivative ends up being 1 over y times 1, which is just 1 over y. All right, so for 3z, there's no x's in it, so that gets treated as a constant. So that derivative is going to be 0. And then for the last term, yz to the 4th gets treated as a constant. So that's going to stay there and multiply the derivative of square root of x. And we've done that one before a number of times. So I'm going to just do that quickly. It turns out it's 1 over 2 square root x. If you don't quite see where I got that from, rewrite the square root of x as a power, as x to the 1/2, and then do power rule to take the derivative, and you'll get that. Alrighty, so that is my partial with respect to x. Next, let's do the partial with respect to y. So for the e term, I need chain rule again. We'll get e to that x over y power times the derivative of the exponent. This time, we are treating x as a constant. Okay, so I'm going to carry this down. So if I'm treating x as a constant, I still don't need quotient rule for this derivative. I've already seen how to rewrite it a little bit as 1 over y times x. And if I'm going to take the derivative of that with respect to y, it's helpful to rewrite 1 over y as y to the -1 and then times that x. But this time, x is going to get treated as a constant. So that part's going to stay there when I do the partial because it's multiplying the y term. So I deal with the y term like I normally would. The power comes down, and then I subtract 1 from the power, and I get -y to the -2. That gets multiplied by the x. Okay, so that's the e term. And now 3z gets treated as a constant, so that derivative is going to be 0. And then for the last term, the z to the 4th root x gets treated as a constant, and the derivative of y is going to be 1. So we'll get plus 1 times z to the 4th root x. So I just need to write z to the 4th root x. Okay, so that's my partial with respect to y. And then finally, I need the partial with respect to z. This one I'm going to do a little bit more quickly. The e term doesn't have any z's in it, so that gets treated as a constant. So its partial is going to be 0. For 3z, that one's just going to be standard. That's going to be 3. And then for the last term, the y and the root x get treated as constants because they don't involve z. So I just take the derivative of the z to the 4th term, and that's going to pop a 4 down. It's going to make the z to the 4th become z to the 3rd. And then the y and the root x stay there because they're constants multiplying z to the 4th. So I'll still have y, and I'll still have root x there. So in the next video, we'll talk about how to compute second-order partials.